So hi everyone, I'm Himshikha. I have Rishab and Arpit with me today, and we are going to be talking about scaling OpenSearch with the next generation shard allocation for high performance clusters. Okay, so on the agenda today we have, we'll first start talking about shard allocation in OpenSearch. How does it work, some of the nitty-gritties of allocation, the components involved. Then we'll go to some of the scaling challenges that we encountered, how we found out some of the bottlenecks, and how did we come up with some of the solutions to solve those bottlenecks. This would involve some deep dive into what it took to get there, what it took to actually be able to scale a cluster, and then we will go to the performance improvements that we observed in terms of latencies and other metrics. In the end, we'll talk about some of the future scope, wherein further optimizations that can be done after the solutions that we've already built. All right, so let's get right into it. Shard allocation. So, everyone creates an index, and then we specify we have, let's say, 5 primaries, 2 replicas set up, and then a bunch of shard gets created on a bunch of different nodes. But what really happens behind the scenes, right? How does a shard get allocated to a node? That is basically the allocation flow in OpenSearch. So the idea is distributing the shards across data nodes to ensure data resiliency, load balancing the shards across the cluster, and basically trying to provide an optimized query and indexing performance. So index creation is just one of the ways where allocation flow gets triggered. There are different changes which trigger this, like index deletions, cluster resize events, node failures, disk watermark breach, basically anything that can actually lead to changing the allocation of a shard. So at the core of allocation, we have a reroute API. This is an asynchronous API which is triggered on every cluster state change event. And behind the hood, it uses a bunch of allocators which actually take the decisions of allocation. Coming to shard allocators. So there are 2 types of allocator. The first one is gateway allocator, which is used for allocating existing shards. Now what I mean by existing shards is, let's say we already have a node and we have a bunch of shards assigned to it, but then that node drops and then comes back in a few seconds. So the cluster manager tries to see, hey, is there a node which already has an in-sync copy of a shard on disk? So if it does find a node like that, it'll just go back and say, hey, you already have this copy, why don't you just go and initialize the shard on the same node. This saves on a lot of resources. We don't have to transfer shard data. We don't have to go through rebalancing again because the shards were already there. So that's basically existing shards allocator. The second one is balanced shard allocator, and this is a more complex and a more granular component because it has a bunch of responsibilities. It takes care of allocating new shards which are unassigned. It takes care of moving shards when let's say a node qualification changes, and it takes care of rebalancing your shards to always take the cluster in an optimal state. So we'll dive into each of these allocators separately. So the gateway allocator at its core has a function to actually recognize what shard can be placed in what node, right? So sometime back we had an unoptimized version of async fetch, wherein the cluster manager would say, like, for every shard it will check with every node, hey, do you have a in-sync copy? Now when you look at smaller clusters with, let's say, 1,000 shards, 10 nodes, 10K calls, and these are like transport calls from the cluster manager to the data nodes. So this is a small number, cluster manager is still able to handle it, everything goes smoothly, right? But when we start looking at a higher scale, let's say we go to 50K shards and 100 nodes, this becomes a huge number, and we've actually seen this in production scenarios where the transport threads start choking, JVM goes high, cluster manager actually fails with out-of-memory errors. So as the number of shards and nodes increase, this becomes like really inefficient, and it leads to cluster manager going down a lot of times. So sometime back, this function was updated to actually do a batch fetch. Now instead of going to every node for every shard, cluster manager will create a batch of shards and then just go to every node and say, do you have any of these shards with in-sync copies? So even if we create a batch of, let's say, 1,000 shards, it decreases the call from 50K into 100 to 50 into 100. So that's like a huge optimization. So this is like some of the pre-work that was done to actually be able to get to a state where we can start scaling a cluster. So that was the existing shards allocator. The next one, balance shard allocator, which as we said is a more critical piece. We're going to look at more details, more granular details of what this does. So shard placement strategy is basically identifying if a shard needs to be assigned and then selecting a node to put that shard on, right? So breaking down the allocator functions, it has three major functions: allocating unassigned shards, moving existing shards because of, let's say, some events, and then rebalancing the shards across the cluster. How this happens in more detail is let's say we decided if the first three parameters are true, right, and we come up with, hey, this is the set of shards that need to be moved. Now how do we actually select a node? So we have like a three-step process, which is decider evaluation, weight calculation, and node selection. Decider evaluation basically goes through a bunch of deciders, I think maybe 20 or more. For every shard, it will check for every node, hey, is this node eligible to take this shard? And it will create a list of eligible versus ineligible nodes. Now, all the eligible nodes will then go to the weight function, and we'll try to give a weight to every node. So this weight is basically a criteria of what are the shards that a node already holds. So like, what are the average number of shards across the cluster, and what is the number of shards on this node, and then what is the average number of shards per index, and how many does this node have. So there are different criteria, there are a lot of nitty-gritties over here, but the overall idea is to have a good distribution of shards across the nodes. Now that the weight function calculates the node weights for all eligible nodes, and then we give it to the node selection function, which basically says that the node with the minimum weight is a preferable node, because that will help me get closer to the average weight across the cluster. So that is how we select a node to assign a shard. Getting into more details of deciders, so allocation deciders are basically a bunch of constraints which say yes or no for a particular shard and a particular node. Right, so let's just go into some of the critical deciders that we have. The first one is disk space based. So the idea is that we specify that, hey, I want to assign only 80% of my disk to the shard. So if I try to assign a shard to a node, if it is already above 80%, the disk decider will say, no, I cannot assign. Or if right now it is at 70%, but allocating a new shard may take it over 80%, then it would say, no, this node is not eligible. Similarly, same shard decider. This is basically to ensure that a primary and replica of the same shard don't end up on the same node, because then it really beats the purpose of having replicas. Awareness decider. So like if you have 3 availability zones in your cluster, it will ensure that we have a good distribution of shard across the availability zones. Filtering decider is basically filtering out the nodes which are marked as not eligible. So as an example, if you are updating your cluster, the old nodes could be marked as excluded, and I want all my shards to go to the new nodes. So the filtering decider will say, hey, this node is not a part of cluster anymore, so I don't want to assign any shard to it. Throttling decider is something that is created to basically control the resource utilization for recovery and relocation operations. So we can say, hey, I have a small cluster, I only want 4 recoveries at a time, so it will throttle if we try to actually move more shards than that at a time. So all of these deciders are basically based on a lot of cluster settings, and we can change these settings based on cluster sizes, the disk space available. So let's say for disk space 80% is default, but I can say, hey, for a node with 1 TB cluster, I'm okay taking it to 90% because the absolute value is still pretty huge. Yeah, so deciders, we discussed this because deciders are kind of crucial for maintaining the cluster health, because if all the deciders say no to all the nodes for a shard, then that shard actually doesn't get allocated and the cluster goes into a red or yellow state. Right, so now that we have an understanding of how allocation works, what are the lower level components, allocators, deciders, we'll go into the kind of challenges that we face with these components. So I'll invite Arpit to talk about it.
Yeah. Thanks, Himshikha. So I will be talking about what are the challenges that we face when we start scaling out OpenSearch, and what are the challenges are there when we are trying to allocate shards on these large clusters. So the very first thing that we see is the weight multiplication start impacting the overall allocation time as well. So let's say you want to allocate a shard. You have to know the weight of every shard, every node that you have in the cluster, right? Now, every node weight calculation depends on how the indexes are distributed across the cluster, as well as how the shards are distributed across the cluster. And it has to also know the constraints which the configuration has to follow, right? So all of that adds a lot when you start scaling out the cluster to large number of nodes. Same happens with the nodes as well, right? Like now a particular shard has lot many nodes to go to because your cluster has become quite large. And deciders are now more complex to actually say yes or no for particular decision. Because now again, let's talk about awareness decider. You need to know in each zone how many shards are present to take a decision whether you can go to it or not. Now we are talking about a large scale over here or a small one. And similarly, we will also have a lot more rebalancing into the cluster, given because it's a very big cluster now. This actually impacts on the allocators as well. So now the gateway allocator, which actually assigns the unassigned shards, will take a lot more time to recovery because you have a large number of shards. Balanced shard allocator will have lot many iterations as well because now you have to rebalance the big cluster, which eventually is affected by the decider evaluation as well, because the decider itself, the very basic unit which needs to be computed for calculating the weight is taking a lot more time. Now, here's a chart where we are trying to say how the allocation complexity changes with the number of shards as well as the number of nodes, because they're a function of both, right? And this is what it depicts. And let's talk about, after this, let's talk about what do we mean by large clusters, right? So to define that, anything between 200 to 1000 nodes is what we consider as a large cluster. It can support to 500K shards into the cluster, as well as it can have petabyte of scale. Needless to say, for such big clusters, you will also need a larger recovery settings as well. When I talk about recovery settings, I'm talking about, let's say, concurrent recoveries, you have primary recoveries as well. And just to give you a scale, let's say you had a primary recovery of 4. Your overall cluster, if it has 1000 nodes, right, it will have 4 into 1000 number of shard recoveries at a single time. That is 4K shard recoveries happening for that cluster at a single point of time. So what does operational challenges it brings to us, the large cluster, right? So the tasks which were easy to happen in a small cluster, they start getting stuck into the queue. We know in cluster manager, we have a single queue which execute the task one by one based on the priority, right? But they start getting stuck over there. The timeouts for the settings start happening now. Now, the simple queries, in a way we are trying to say that the simple setting updates or the index creations, all of them start becoming complex and time consuming as we scale the cluster, right? So, let's talk about what are the common operations that we do for a cluster. We do index creation, the CRUD operations, we resize the cluster based on the disk and whatnot. We want to add nodes, we want to remove the nodes based on if there is any hardware failure or not. You would want to do a rolling restart for a cluster upgrade, or you would like to do a cluster manager restarts as well. Basically, you also would like to do a cluster setting update, basic cluster setting update. Now, before going to what goes wrong, let's also, I will try to explain what is the setup that we try to understand. We tried to create a 1000 node cluster and we had 500K shards on that, and we did a cluster restart. we started thinking about what will happen to that cluster and how it will impact your cluster manager. But because that's the main thing which is going to do all the tasks, right? So the very first thing we started seeing that the pending task started waiting for a long time. And more or less it was getting stuck at the cluster reroute task, where we were seeing it was taking even hours. It's just for instance, we have taken this particular case. We started debugging more into why reroute was started taking time. Now, think about reroute. You had 500k unassigned shards at a moment. You have to assign each shard across all the nodes, and you have to do it one by one. So for each shard, you have to go through all the 1000 nodes. Every node, you have to go through all the deciders as well. So it's like 500k shard multiplied by 1000 number of nodes, multiplied by the number of deciders that you have in your cluster, right? So that becomes very computational heavy for a big clusters, like 1000 shards, 1000 nodes and 500k shards, right? What it leads to, your normal operations like cluster setting updates, they start timing out because now they are in the queue and they are just waiting for cluster reroute to happen. Adding more to what I was talking about, your normal operations like cluster setting updates, which are time sensitive and they need to happen within a minute, they start failing. Your index creations, which are normal operations, they start failing. Your admin operations are almost blocked, and your cluster is now unmanageable because you cannot update any setting and you cannot do anything with the cluster. So in basic terms, if your reroutes start taking more time, you will start seeing timeouts. That means, in a way, failures, and which will lead to a cluster becoming unmanageable. You can also say that the long-running reroutes actually paralyze your whole cluster management for that moment. Now, let's talk about what are the traditional approaches which leads to this particular issue, right? So the very first thing is the reroute task or any task in cluster manager at this moment are not time bound, right? It can run for hours or even for days when they are getting executed at that time. And which is what is happening in the reroute case as well. Now, when that happens, the higher priority tasks, even if they are present in the queue, they will still get stuck because the cluster manager, being a single queue, is busy running one particular task. And we also do a lot of wasteful work while doing the reroutes. So just to give an idea of that, assume you have 500k shards and 1000 node cluster, right? You had a recovery setting of, let's say, 32 that you can have concurrent recoveries. You can allocate at max 32k shards on that cluster, but the current allocation logic will still compute for all the 500k shards. But in the end, you are only going to allocate 32k shards for that particular iteration, right? And that does not make sense, and that's a lot of wasteful work that we do. Again, this is the diagram which tries to say that how cluster reroute can cause issues with the cluster. You have a cluster reroute which is running for more than 10 minutes. Your node join, which is more critical to it, also get blocked. Your setting updates also get blocked. And even the index creations, everything get blocked in that cluster, right? Now that we have discussed about what are the problems that are there with the large cluster, I would like to welcome Rishab to talk more about how we can solve it further.
Yeah. Hey, thanks, Arpit. So let's start with expensive allocation deciders. As Arpit talked about, reroute is currently taking a lot of time. It takes more than 10 minutes with the current unoptimized behavior. And during this, while we were trying to analyze what kind of problems that these allocation deciders currently have, we identified, if you see in this particular flame graph, there are very silly issues that are currently present in the allocation deciders. This is one of the examples. This is the flame graph of trying to profile shard allocators that happen in a reroute method. The deciders that is there is the disk threshold decider is consuming a lot of time with string format. A lot of this time is just spent in string formats. Coming back to the allocation deciders profiling, if you see the first one, the awareness allocation decider, that is currently taking 77.1% of the total CPU usage by the master by just doing some compute in the under capacity method. The second one, it is just probably checking the average disk usage and consuming all of the master CPUs, all the CPU cycles that the master has. Coming to the third one, The throttling allocation decider can allocate method is taking 91.6% of the CPU, which is again almost choking the master thread. The CPU is just choking out just because it's trying to run a method which is doing nothing but checking doing a string format not in a optimized format. So let's try to break it down. What are the problem areas? Deciders are currently heavy compute. The logics are very complicated. And the problem with the allocators is they have unbounded operations, as Arpit talked about. It currently goes on and on to run beyond 10 minutes, which is probably can be broken down into multiple subtasks instead of running it in one go. And they were already doing wasteful work, so we can cut short that as well. It takes more than 10 minutes of runs. The reroute operation taking more than 10 minutes was blocking all the high priority tasks, which was higher than the reroute. For example, the node join operations, which was an immediate task that was supposed to be executed but couldn't just go through because reroute was running on and on and on. So what are the solutions? Coming to the allocation deciders, we need some approach which should be optimizing the logic, which should execute much faster, not just bottleneck and choke the master thread completely while running those set of operations, although not compromising on the feature or the solution that the particular decider was performing. And it should have, obviously, it should have better flows. It should not touch how the allocator was currently running. Second, the time-bound allocators. The allocator was running for more than 10 minutes again, coming back to that. Reroute was running more than 10 minutes. It was not deterministic. We never know that how long the allocator will go on and on and on and on. So we need to control that. We need to make it time-bound so that the iterations can complete faster and other priority tasks, if pending in the queue, should just go through. It should not block the cluster operations. So let's dive into each. Allocation decider optimization. The first one, if you see the throttling allocation decider, the problem was just the expensive string format, which was doing nothing but when not in the debug mode, where it just doesn't need to send a message back to the user, it was still doing a string format calls. So what was the solution? We skipped the unnecessary string formats that was happening not in the debug mode. If a user hits the API of cluster allocation explain, which has to run in the debug mode and needs to give back the user an output, it would still run in debug mode. There we would probably, is okay to do a string format call. But when it is just for the master purpose and whether the shard can be allocated on the node or not, we don't really need to do that. This itself gave us 40% improvement by just avoiding this unnecessary string format calls. Coming to the second one, shard limits decider. It was inefficiently parsing the cluster setting which was not needed. Every single time, every shard that needs to get allocated on a particular node, it does a setting parse, which was again getting a bottleneck. By just caching the shard limit in metadata, we were able to reduce the reroute allocation decider runtime, a total runtime by 10%. Second, the third one, the disk threshold decider. Every single time a shard that was supposed to get allocated on a node, while it was checking that, it was unnecessary iterating over the disk usage of every single node to calculate the average disk usage, which was again not needed. It could be simply cached because while you're allocating such high amount of shards, that stays consistent. So this is what we did. We cached the average total bytes and average free bytes inside the cluster info. That gave us nearly of 8% improvement. Awareness decider. The get function call for a hash map where key stored as a string, there were multiple such calls. Every single time it was doing, for fetching the same info, it was doing the same calls multiple times. It was again not needed. It was unneeded. We tried to optimize that. We cut short those many calls, cached them in the decider itself so that unnecessary usage of get calls reduces. So that was not needed. This gave us 10% of improvement. Now, although these kind of helped us to reduce the reroute time by a lot of margin, but still, if we could see, the operation was currently running for more than 12 minutes. Even if we cut short by 50%, we are still at 6 minutes, which would kind of not help us to again go on with cluster settings update, because the timeout there is just 1 minute. When you hit a cluster setting update call, you have to execute that task within a minute, or for that matter, index creation operations, unless you specify a custom timeout. So we tried to make the reroute iteration time bound itself. So the key changes that we did, we time boxed the reroute iterations. every single reroute operations, the allocator that we earlier talked about, the gateway allocator and the balance shard allocator were made time bound, so that every single time a reroute operation occurs, it has to finish off in the specified time limit, and a subsequent reroute will take up the task which is pending by the current allocator. So how does this help? A reroute operation which was probably a high priority task will let a urgent priority task pass through as soon as it completes. For example, if the timeout given to the reroute operation is now, let's say 40 seconds, within 40 seconds, this operation will conclude, and in the next 20 seconds, the next operation can be picked up, which is higher in the queue and pending in the pending task. So this will again help us with the API timeouts, the cluster setting updates call will go through, the index setting, index deletion operations will go through. This will again, successful index creations during recoveries will happen, and these changes were introduced post 2.19 OpenSearch version. What are the benefits? Now we have predictable operation times. We know that within what time range a reroute operation will conclude, be it gateway allocator or be it balance shards allocator that we earlier talked about. The cluster management will now be responsive. We know, and it's predictable, that how long a particular operation of a reroute will gonna take. No API timeouts during longer recovery, long-running reroutes, and this will obviously give us better cluster stability. Your admin task will not be anymore blocked. The reroute loops will get faster. Now, so if you see here, now earlier where it was 11 minutes, 12 minutes of a reroute cluster, the cluster reroute task was going on, with a 1 minute timeout, with a 40 seconds timeout that we added for the gateway allocator, we can now see that it's now taking 44 seconds, 44 seconds, 41 seconds, and things like that, which is less than a minute. So this will not block any of your admin operations, be it cluster settings update, be it index creations, be it node removal, node join, and things like that. How you can tune those settings? So now we have, now that we have made this optimizations, we can obviously tune those settings, make it customizable as per your cluster needs and your index creation timer that you supply. For example, shards batch gateway allocator, which allocates the primary shards, can be given a 20 seconds timeout. This doesn't mean that after 20 seconds your shard allocation would stop. It just means that a next task in the queue, which is higher in priority, will probably get executed. Post that, this particular reroute will be picked up again with another 20 seconds of timeout. Similar for replica allocator timeout, and similar for balance shards allocator timeout, which allocates unassigned shards or move shards or rebalances shards. Again here, now if you feel that this is probably hampering your cluster, you can also schedule a subsequent reroute. Since now you have cut off the first reroute that was happening, let the higher priority task pass through. You can now instead also, and if you feel that this is ideally blocking your shard allocation, you can again put the subsequent reroutes at a higher priority, so that as soon as this particular task finishes, your subsequent reroute that is going to happen is picked up immediately. Or if, for example, if you give this scheduled reroute priority as high, and if there is a node join task that has come up with an immediate priority, would be executed first, obviously. So, and this task will be picked up later if it is next in the queue. So let's talk about the performance improvement that we have gotten. As you can see, this is a scenario for full cluster restart. Earlier, with no optimization at all, it used to take 232 minutes as the baseline for a full cluster restart. I'm talking about allocating 500K unassigned shards here. With decider optimization that we talked about, which helped us cut short the decider runtime, we were able to get down to 119 minutes to allocate all the 500K unassigned shards. Post the reroute allocator, time bounding the allocators that we have added, we were able to allocate all the unassigned shards. I'm talking about the empty shards here. All the unassigned empty shards within 40 minutes. Talking about the reroute processing time, earlier the P99 was 11.52 minutes that we could see. After decider optimization, it went down to 4.9 minutes, and post the time bounding allocators, we were able to get down to 40 seconds. Index creation, which was still not succeeding with decider optimizations, and in the baseline, obviously it was failing if you had 500K unassigned shards. With time bounding the allocators, the index creation always went through. Similarly, the time to green, the primaries recovery, the time to yellow, I mean all the primary shards getting assigned. Earlier it took 93 minutes, with decider optimization it took 49 minutes, with time bonding the allocators it took only 14 minutes. During zonal failure scenarios where, let's say you had a partial zonal failure which led to 60,000 unassigned shards and a lot of nodes in a particular availability zone was dropped, with 60,000 unassigned shards getting created. Earlier, the recovery time with shard allocation was 108 minutes. After our optimization, it went down to 10 minutes. Reroute processing time, which was nearly 8.8 minutes, it went down to nearly 30 seconds. Index creation, again, which was not able to go through because if the reroute itself was taking 8.81 minutes, your index creation task or cluster update setting task will not go through. But with our optimizations, and because the reroute processing time itself was 30 seconds, the index creation and deletion also passed through. During node drop scenarios, you would not see a lot of improvements. Again, because let's say for in a cluster with 1,000 nodes and 500,000 shards, and if you dropped your 12 nodes, which led to, let's say, nearly 4,500, 5,000 unassigned shards, since the shard count is very less to allocate, you would still have very near equal shard allocation time because the number of shards to allocate is still very less. The reroute processing time was obviously within the range, since you don't have a lot of unassigned shards to get to allocate. The index creation and deletion were passing in all the behaviors. So all in all, this enhancement that we have done seen more fruits while you have a lot of unassigned shards, when there is a cascading failure in your clusters, when you have large number of shards and the number of nodes are also decently high. So summarizing the improvements that we have done, decider optimizations, optimizing the throttling allocation decider helped allocation time improve by 40%, as we have seen earlier. Caching the shard limit improved the decider runtime by 10%. Optimizing the data structure in zonal decider improved the allocation time by 15%. And pre-computing and caching the disk stats helped us gain approximately 8% in the allocation runtime. The improvement that we have gotten in the allocation or allocator orchestration, which is the time bonding the allocators, during the full cluster restart, it was significantly improved. There was a 93% improvement in the cluster state processing time. Time bond the existing allocator batch allows higher priority tasks to pass through, again because now it is not anymore blocking higher tasks because in itself it is getting finished up in less than a minute or depending on the timeout that you have given. Time bonding balance shard allocator also improved allocate and assign move and rebalance, as we have seen in the zonal failure that we had. And optimizing the allocation constraints on average primary shards on all indices. This was another task that we picked up, which was optimizing the allocation constraints to have near equal number of primary shards on each node. So coming to the future scope now, this was the improvement that we have done, which significantly improved, but there are obviously a lot of items that we can pick up which would further enhance and reduce the complexity of our allocators today in OpenSearch. One of which is enhancing the parallel processing. Currently the decider, as we spoke about earlier, the decider sequentially analyze per node per shard chains to evaluate whether a shard can sit on a particular node or not. We can probably take up parallel processing here, which would reduce runtime of the entire allocator. We are also planning around advanced queue management, which would implement specialized task queues so that each task queue can operate independently, be it higher priority task or urgent priority task. Currently the shard allocation strategy is greedy in nature. It goes one by one and then subsequently and eventually it identifies whether a later shard that comes in the allocation picture would be able to get allocated or not. It doesn't see the full cluster view while allocating all the shards. Probably this is an important piece of work that we might pick up, which would be intelligent allocation strategy. Moving from single shard greedy algorithm to cluster-wide optimization model. And another one is optimized recovery process. So with remote store, I think we can already have, during, let's say, when there is a full cluster breakdown and you have a lot of unassigned shards, with remote store, we can already have an idea which shard was allocated on which node. Probably that can be used to optimize the recovery process in general, instead of going to again the the decider chain that we had, which was even optimized but still complicated. So that was our future scope. That's it from our presentation, but if you guys have any questions, we are more than happy to take that.
Yeah.
What show the results? Those two charts. What is the cluster size?
This was a 1,000 node cluster with 500,000 unassigned shards.
And then the other mentioned optimization is already OpenSearch.
Yeah, it's an OpenSearch. 2.99 onwards. Yep. Yeah. There is already a possibility for custom starting strategies. The allocator in OpenSearch is built in a way where you can plug in your own allocators and assign it through a particular settings. So a lot of users already do that, but then again, you have to write your own set of allocators and own logics to have that.
You were deciding kind of how often to update the cache, the total byte size after you decide that?
Every cluster state update does that, but what are you saying?
Which one?
Every cluster state update updates the byte size, that the disk usage you mean, right? Every cluster state update, it's get updated.
How often?
It depends on your cluster operations that you are running. If you are running very frequent cluster settings update or very frequent index creation operations, node join and node removals, it depends on that. But as and when your cluster is updated, your cluster state is updated, it will the cache will also get updated. Yeah.
So one thing I'm really interested in is how did you, these ideas are really innovative, but how did you come to some of that? So I know you looked at this play program, but what made you think of some of the approaches, like for example?
Got it. How did we come to the solution is what do you mean? So again, it was while we were trying to experiment through a 1,000 node cluster, we could very easily see during a full cluster restart, the reroute operation was taking too long. During our profiling runs, it could come out very easily that there are deciders which are very expensive. Optimizing that still didn't give us the result because any index operations or any cluster admin operation that you have to compute has to complete within a minute, right? Whenever they start to execute. So any operation that you run has to finish up within a minute. That is where we came to the solution that probably time bonding a reroute operation and scheduling a subsequent reroute so that urgent priority task can pass through is probably a better solution that we could have. That kind of gave us that idea.
So when you're time bounding these operations, where do you keep the state of when the task was?
I didn't get you.
Right. So you're time bounding these operations, right?
Yes.
So when it types out, and then how's that managed? Is it in the queue, and then how does it keep track of what it's doing?
It goes back in the queue. Yeah.
Because you schedule a subsequent reroute as well. Whenever you finish up a reroute and if there is a pending assigned shards pending or there is a pending move pending, there's a queue maintained already which has already scheduled a subsequent reroute in a priority that you probably want. So for example, let's say the next scheduled reroute is at a high priority. Meanwhile, if there is a node join task that comes on, if you are trying to add a node, which is probably an immediate priority task, will go through and then your subsequent reroutes will pass through. Any more questions, folks? I think we are almost also out of time. Thanks, guys.
Yeah.